In this lecture, we're going to discuss a very versatile proof strategy, which is known as proof by contradiction. So suppose we're trying to prove something. So we're trying to prove, what do I mean by something? So a proposition. So a proposition, let's call it P. And so we can try things like a direct proof, a proof by contrapositive, things we've discussed. Another idea, so one idea is the following. So suppose that the thing we're trying to prove is false. So suppose, for sake of contradiction, that the thing we're trying to prove is false. And here's the reason we might want to do that. A proposition, remember, a proposition by definition is either true or false. It has a definite truth value, right? So it's either true or false. We want to prove that it's true. If we suppose that it's false, and then we somehow proceed logically and arrive at a contradiction, well, then we'll actually know that it couldn't have been false, so it must have been true. So let me write that out. So we'll suppose that the thing we're trying to prove is false, and then we'll try to derive a contradiction. Derive a contradiction. And remember, a contradiction just means a statement that's always false. So for example, the kind of typical example is Q and not Q. Well, those cannot both be true at the same time. So this is always false, no matter whether Q is, if Q is true, this is false, evaluates to false. If Q is false, this evaluates to false. So you try to get a contradiction. Something like 1 equals 0 is another example. Okay, well, we got a contradiction. We always assumed that P is false and just proceeded logically. So since P being false, led to sort of a nonsense conclusion, so led to a contradiction, something that can never be true. What's our conclusion? P must have been true. P must have been true. Which actually completes the proof. It's a really interesting idea. And again, it's because the proposition is it's either true or false. It can't be both. It can't be a mix of the two. It's one or the other. We assume it's false. That's what we start by doing. And then try to derive a contradiction. That actually proves that it must have been true. So it's sort of an indirect proof technique. Here's an example of that. Let's try to prove the statement, no integer is both even and odd. Both even and odd. Okay, well, it seems fairly obvious, but how would you actually convince somebody? How would you actually go about showing this? And one of the most natural ways to do it is actually this idea of trying to get a contradiction. So we assume otherwise. So we assume, for sake of contradiction, it's often useful to kind of point out to the reader that you're about to do a proof by contradiction. So putting in a phrase like that. Assume for sake of contradiction that, well, what is the negation of this? It would be that there is some integer that's both even and odd, right? There is an integer. Let's call it something. You often want to give things a name, so then you can proceed further. So there is an integer x that's both even and odd. Even and odd. by the way, just to kind of drive this home, so no integer is both even and odd. What is this really saying? Like if we put this into logical terms, so is not is not the case that there exists an integer that's both even and odd. So it would look like this if we were going to write this kind of using our formal notation. It is not the case that there exists an integer that's even and odd. Is even and odd. And so the negation of this, right, if we put another, use red, we put here, I'll use this. So if we put another symbol, that always cancel out here. So the negation is, yeah, there exists an integer that's both even and odd. Okay. So what does it mean that x is both even and odd? It means that x equals 2 times an integer, and at the same time, x is 2 times an integer plus 1. That's our definition of odd. I'll call it something else, right? We don't want to assume it's the same, okay? Okay, right? For integers, k and l. Excellent. Okay, and now, so we assumed that our proposition was false. We are going to try to get a contradiction here. And, I mean, the only thing I can really think of doing, sometimes you just have to kind of follow your nose. The only thing I can think of doing is setting these two things equal, right? Because they're both expressions for x. And, I mean, yeah, this seems suspicious, right? We have an even number over here. We have an odd number over here. But, again, how do you actually prove it? Well, let's divide by 2. So what k is going to be l plus a half. But k and l are integers, right? So you can never have this. You can't have. I guess we want to be really clear. Let's divide. Let's move the l over. Nice. Okay. So here we see this thing over here is an integer, right? So k minus l is an integer, and k minus l is not an integer, right? So basically we showed, yeah, k minus l is an integer. Why? Because it's a difference of 2 integers. That's going to be an integer. But also we showed that k minus l is not an integer. So there's our contradiction. And because we just proceeded using valid logical mathematical steps here, we just have to, I mean, the only thing we assumed is that there is an integer that's both even and odd. So that assumption is false. So yeah, so since, just to finish writing this up, so since assuming our proposition false led to a contradiction, the proposition must be true, the original proposition. And that concludes the proof. Yeah, so there cannot be an integer that's both even and odd. Okay, great. One other thing, so notice that this statement here, it was not in the form of an if-then, so it wasn't an implication. What if we had an implication instead? So what if we don't have an implication, you just assume this is false instead of true, and then you try to get a contradiction. But what if our proposition has the form of a conditional, if-then, of a conditional statement? Right? So like this kind of thing. P implies Q. Can we still do proof by contradiction? Absolutely. It's the same idea. So in this case, then we start by assuming not that P is false, but we assume that this statement is false. This proposition that P implies Q is false. What does it mean for this to be false? Well, if you remember the truth table for this statement, this is only false when P is true and Q is false. If P is false, actually, this is going to always evaluate to true. Remember, it's a little bit counterintuitive. But yeah, what we want to end up doing is, so yeah, i.e., we assume, how do we assume this is false? We actually assume P is true, but Q is false. So P is true, but Q is false. That's what this means. So if we assume the conditional is false, that's assuming this, okay? And then we do the same thing. So then try to derive a contradiction. And this works just as well. Just want to emphasize this. So you're not, if you have a conditional, you're not actually assuming P is false. You're assuming the whole statement is false, which is this: P is true and Q is false. Let's do an example just to show the idea. So example, let's do a slightly more complicated one. So maybe one that's not super obvious. Just looking at it, because yeah, I mean, this is the type of thing that you can just look at a statement and immediately say, like, okay, it's obviously impossible. But yeah, technically, if we had to write it up formally in a very convincing manner, this is one way to do it. This is extremely convincing here. So next example, let's say if A, B, and C are integers, satisfying the following equation: A squared plus B squared equals C squared. It's like the Pythagorean theorem. Then the conclusion is A or B is even, which is actually not very obvious at all. I mean, maybe if you've seen some number theory, you might see why this is true, but yeah, I don't think this is an obvious statement at all. So what integer is satisfying this? That has a name actually in number theory. They're called Pythagorean triples. This is not necessary for this problem, but just to point out. So Pythagorean triples. Pythagorean triples are specifically integer solutions to this equation. So for example, 3, 4, 5 is a Pythagorean triple corresponding to the right triangle with sides 3, 4, and 5 in the Pythagorean theorem. And there's some other ones like 5, 12, 13. Obviously, we can multiply one by any number, and that will again become a valid solution. I say obviously just because that's essentially scaling this triangle. So it should still be a right triangle. But also you can prove, from this equation, if you scale anything, you can just kind of factor that out and cancel it on both sides. But you'll notice here, it seems like A or B, at least, is always even. So here to 12, here to the 4. Here both A and B are even. That's okay. Remember, our OR is always an inclusive OR. Okay, so this actually seems a bit tricky to prove. So it's essentially saying you can never have like 7 and 13 that both as my two sides. It's saying that the other thing will never come out to be an integer. It'll always be maybe a square root of something. Okay, well, the idea is going to be, one way to prove this, probably actually the easiest way to prove this, is a proof by contradiction. So let's just make sure we know how to set this up. That's the important thing. So here's my if, okay? So it's if we can kind of pull this part outside of the if we want, but so this is just part of our setup. But if this is satisfied, right, that's the key. It's not just that they're integers. If they satisfy that equation, then A or B is even. So it's like P and Q. Okay. So again, for the sake of contradiction, I always like to point out that we're going to do a proof by contradiction. It's very helpful for the reader to follow, as people are going to be reading your mathematics. So, for the sake of contradiction, what is the negation of this? It's that this is true. So yes, they do satisfy this, but one or the other is not even. So in other words, both of them are odd. So for the sake of contradiction, suppose P and not Q. That's what I want to say. So suppose A, B, and C satisfy, so integers, satisfy A squared plus B squared equals C squared, but A and B are both odd. Right? I guess I'm technically using De Morgan's law here, right? So A is even or B is even. The negation of that would be A is not even and B is not even, right? So A is odd and B is odd. Okay. So this is really important. Just to get to this first sentence here. So we're assuming P, but not Q. P is true, but Q is false. Okay, and now we have this set up for the rest of our proofs. So now we can get to work, right? This is what we're assuming, they're both odd. So we'll have to use this somehow too, but let's start with this. We know how to deal with this. So suppose, what does it mean for them to be odd? It means that A must be 2 times an integer plus 1, and B must be 2 times an integer, possibly a different integer, plus 1 for integers K and L. So for K and L in the integers. Okay. Okay, now we can get down to business here. So, what else should I do with these other than plug them into here, right? So let's plug them into our equation. Because again, we are assuming this is true, right? This is true, but this is false. So they should still satisfy this equation. That's what we want to assume. So we will plug them in. And this equals C squared. I don't know anything about C yet. It's got a square there. Okay, let's expand this out. Again, this is the part where you just kind of do the only thing you can. And then once I've expanded this out, then I can start thinking. Plus 1 equals C squared. And so we're going to get 4 times K squared plus K plus, kind of factoring out little 4s, plus L plus, I guess, 2 equals C squared. Is that going to help? Let's see. Do I want to factor this out? Not sure. Yeah, let's stare at this for a second. So now is when we can start thinking. I'm already noticing something a little bit fishy here. So in fact, let's think about even and odd. So I have an even number plus an even number. That's even, right? So C squared is even. So C squared is even. Rather than writing this up really clearly, I'm gonna focus more on showing the thought process, because that's the important part. So C squared is even. I think what we already showed is that actually implies that C is even. And just to recall why that is, if C were odd, then C squared would be odd. And again, that's because if you square something like this, you get 4k squared plus 4k plus 1, which is an odd number. Right? It's 2 times. Yeah, I do remember doing this in a previous video. That's an odd number. It's 2 times an integer plus 1. So we prove the contrapositive here, right? So if c is odd, then c squared is odd. Therefore, if c squared is even, then c is even. So this is neat. We're actually using things that we've done before. Okay, well, c is even. Is this going to get us anywhere? Well, that narrows down the choices for c at least to half of the integers. Well, c is even. Let's take advantage of that. So let's let c equal to be 2 times. I already used k and l. What's after l? M, I guess. Okay, and then c squared is 4m squared. Let's plug that in. So then I feel like we can cancel out these 4s and something interesting might happen. Okay, I'll come down here. So, yeah, let's write this side out again. Plus L squared plus L plus 2 equals 4m squared. Okay. This is kind of funny. I feel like it's going to end up being the same as that. So what if we divide by 4, and then what if we divide by 4, and then move everything to one side? I guess there are other ways to get a contradiction too. So like this side, I'm already saying this is a multiple of 4. This part is a multiple of 4, but I'm adding 2. So actually this is not a multiple of 4. And this is a multiple of 4. So we already see the contradiction here, right? But I guess just to make it super clear like we did above, we can move everything to one side. Move all the variables to one side, and move the half to the other side. I need a negative half. That's okay. Okay, and then we have integer, not an integer. Contradiction. This is a contradiction. And yeah, what's the conclusion? Our assumption was false. Our assumption that this whole conditional statement was false ended in contradiction. Okay? Which means this whole conditional statement is true. Which means if I have integers satisfying this, then one of them has to be even. Okay, so that is an introduction to this important proof strategy, and we'll definitely add this to our toolbox and use this many times going forward as well. All right, thanks for watching.